In the last class, we saw about CNN architecture and how we could implement the architecture, right? We made a basic CNN model, and using that we solved the problem of the MNIST dataset. In fact, we got very good accuracy as well. We got 98% accuracy, which is great. So we understood this and we know how we can add a CNN layer, right? Now that we have understood this, what we will be understanding next is transfer learning. So obviously we know what transfer learning is. So just a summary, a quick sum back is, see, when you are having these models are like have like 60 million, 138 million, these are the number of trainable parameters that are required. So you cannot sit there and for every time train the whole thing just so that you can satisfy your particular product, or you can satisfy and get a particular answer or a model. So that is not possible. Hence we have the concept of transfer learning. So what transfer learning does is, basically, instead of going through everything in details of what is happening and training the whole thing, we just train only a part of the model. So the final few layers we will be training and the rest we keep constant. These constant layers have been trained earlier by the author, by the researchers who have come out with this model. So we have the weights that have been used, and so we use these weights, we do not train these, and the final layers we will be training. So everything will be the same, the forward pass will be the same. Instead, these here, it will the weights will remain the same. In backward propagation also, you will propagate only till the weights have to be trained. Beyond that, there will be no backward propagation. So that is the whole thing behind this transfer learning. So what we will do right now is, we will go through our very first project. So our very first project is basically cats versus dogs. So you have this data set. This data set contains images of cats and dogs. So what you have to do is build a model using transfer learning, obviously. So you can use any model there, any architecture that has been pre-trained. So using transfer learning, you will build a model, and the main task of this model will be to classify whether an image is cat or dog. So you will have to go through it, and then you have to save like you can understand obviously, but is your model able to identify that? So that is the whole task. But we will not be building a CNN architecture from scratch. We will be doing it using transfer learning. We will be doing that using VGG16. If you don't remember the architecture of VGG16, I highly recommend to go back and understand about VGG16 again before you come and understand the future of whatever will be happening in this code, right? So the very first thing that we will be doing is, right, we will be using a Google Colab. So what I am trying here right now is to use both your Jupyter notebooks, your local system, as well as make you familiar with the Colab system, right? So this is the whole thing behind it. Anyway, so you have all this, and I have written everything what has to be done. So the very first thing that we will be doing is, right, we will be moving into the drive, in my drive, and in my drive we will be saving and doing everything else. Okay, so we will be changing the directory to my drive here. So you have the command cd my drive, and then there you go. So you are now in the drive. Now in this drive, what you will do is, the very first that you have to do is download the dataset. Now this time your datasets are not from the Keras system itself. You do not have it in this framework. Now you will have to actually download the dataset. So you can download the dataset from Kaggle. So here you have this dataset here. You can download it from here. You have the link here present. Okay, so you can download the dataset from here. Once you have downloaded the dataset, right, it will look something like this. So this is your zip file of the dataset. When you extract it, you have this train folder and test folder. In these folders you have images, right? So that is the whole thing behind it. So if you look here, So this is the whole thing. Once you extract this, you have a train, a test, and inside train you have just random images. Okay, let's look into test, you will understand that. So you have images of dogs and cats and everything together. So this is basically the whole thing about the data set. Okay, and then you also have a sample submission.csv. What the sample submission.csv basically contains is, so this is what the sample submission contains. So it has the ID of an image and it has the label. So 0 symbolizes cat and 1 is for dog. Okay, so you have this here. This is what sample submission means. Now what we will be doing is, once we have downloaded it, the very first thing that we will do is extract it. So this is the code to extract the whole file, right? So you can start from here. So from zip file, import zip file. Now zip file is basically to extract all the zip files. So once you have downloaded it, it will be in this zip folder, in this dogs versus cat.zip. So you need to extract that. So you define an object for the zip file, and that object will now extract everything that is inside dogs versus cats. Once you have extracted that, you will get two folders, test and train. Okay, now you have to extract the train and test folders also, because in those folders then finally will you have the images that are required. So here we are extracting the train folder in the same format. So you are using zip file and you have defined an object for zip file. Once that object has been defined, you can define what zip file you want to extract, and then you can do an extract all. In the same way you are extracting the test1 file. Now the thing about this is, see, you have the whole thing. So right now if you see, your data set will probably look like something like this. So you will have data set dogs versus cat. Sorry, so what you will have is, you will have a train and then you will have a test. You will have two folders in this format. Okay, inside train you will have photos of dogs and cats. So all this is together, right? We will not be using test for now, we will just be understanding using train. So in train you have photos of dogs and cats. To actually train the model, what you have to do very first thing is basically separate the cats and dogs photos. So you will have two directories. One directory will store all the photos of the cats and another file will store all the photos of the dogs. Okay, so that is our very first task after extracting it. So it has to be in this format, if you see, right? So you will have one folder called dataset dogs versus cat. In that folder you will have two folders. One folder is for train, one folder is for test. In train again you will have two subfolders, dogs and cats. Dogs will contain all the photos of dogs, cats will contain all the photos of cats, and in the same way you will have the same thing for test. Okay, so we are creating a directory of this format. Okay, so this is a very first task after extracting all the files. Now before we separate out the photos of cats and dogs, we have to actually create the data set. So here what we are doing is basically we are make dirs is used to create a data set. Okay, and we are creating data set new dir, and this new dir is basically dogs and cats. So dataset home. So dataset home is basically dataset cats versus dogs. In that you will have a sub dir which is subdirectory. So in dataset cats versus dogs you will have two subdirectories, train and test, and in the subdirectory again you will have two different subdirectories, dogs versus cats. Okay, now are you understanding? So the first time what will happen is you are having two loops here. So the first time it will select a subdirectory. So the subdirectory, let's say, is train, the first subdirectory that is selected. So I have selected train. Now it defines a list which contains the two label directories, dogs and cats. So we will now select the first label directory, that is dogs. So we will create a new directory which is in dataset dogs versus cats. Inside that you have a subdirectory that is train, and then our label directory which is dogs. So you have the dogs directory inside the train. In the same way, the second time it will create a cats directory in your train, and the next time what will happen is, now that this loop has been done twice, we will go back to the subdirectory. In this here, what will happen is we will be choosing test. Now in test, again we will create dogs and cats as the two label directories. Okay, so this is basically creating of directories. I am not running this. The reason why is I have already created it. You can see you have dataset dogs versus cat. You look here, see you have two directories, test, train. Inside train you have cats, dogs. In the same way, inside test you have cats and dogs. So you can see this is basically the structure that we are looking for. So the data set, even though you have the data set and extracting the data set gives you test and train, but in the test and train also you have to basically subdirectorize it based on what label it is. So it is a cat, you have to put it in the cats folder. If it is a dog, you have to put it in the dogs folder. So that is not done here, but that is what we will be doing. Okay, so that is the whole thing. Now that you have created this kind of structure, this file structure, what you will be doing next is basically, now you will be actually shifting everything from one place to the other. That means you will be actually, from the actual data set, you will be shifting your dogs photo to dogs, cat photo to cats, and so on. You'll see what is happening. Okay, so now what we are doing is, first we will, like I said, if you remember, that we will only be using the test for now, the train for now, I'm sorry, we will not be using the test data for now. Okay, so this test also is created from the train data set. We are not using the test one as of now. So what is the very first thing we do is we divide into validation ratio. So let's suppose, what that means is, let's suppose you have 50,000 images, right? So you have 50,000 images of cats and dogs. So when you define a validation ratio of 0.25, what that means is 0.25 of the images will be used for validation. Okay, so that means 25% of data is validation data. So that is what this 0.25 means, validation ratio, sorry. So it is the validation data. So 25% of our data will be used for validation. The rest we will be using, rest 75% will be used for training. Now you define the source directory. So the source directory is basically from where exactly you will be shifting the data. Now like I said, see, this is our initial format. You need to understand this properly. So we have train, and in train you have photos, photo 1, photo 2, photo 3, photo 2, 4, so on. Okay, so you have pick 1, pick 2, pick 3, and so on. In the same way you have one test, and inside also you have the same thing. Here you have no divisions of dogs or cats. Now what we want to achieve is dataset underscore dogs versus cats, and in that we have train, and in train itself we have dogs, cats. In the same way we have one test, then again dogs, cats. So this is basically our whole structure. So what we will be doing now is, we will be listing, since we will not be using test anymore, we are using only train as of now, and this train has been used, this train we will be using to divide it into train and test. And what will be the ratio? In the test you will have 0.25% of the 25% of the images. In train you will have 75% of the data, right? That is what it means. So what we will be doing now is, from this folder, train folder, we will be shifting it into train and test. Okay, so that is what we will be doing here. And train and test, not just train and test, we will also be seeing whether it's a dog or cat according to the labels, and we will be shifting it in whichever category it requires. So that is now what we will be doing. We have created this structure, but we have to shift from our original structure into these structures. So we have the source directory, which is the train directory, this directory. Then we have our dataset home. So home dataset is basically where you want to, this main directory is your dataset home. Okay, now what we will do is, for files in source directory, so for every photo that is there in train, what we will do is, we will extract the source, and we'll have the destination directory. So DSTDIR means destination directory for short. It is train slash this train. This is our destination, this is our source. Okay, so we will be checking now first if random value is less than val ratio. So this is just a basic random check, nothing much. So this will be basically used to randomly divide into train and testing folders. So to randomly divide it into this train and test folders, we will be using this simple check, simple if statement. Okay, so here what will happen is it will randomly give you values between 0 to 1. Okay, so if your value is less than 0.25, it will go to test, otherwise it will go to train. Okay, so that is what this means. This is basically to divide it into equal formats but also randomly. So in that case, what will happen, if it is less than 0.25, your destination directory changes to test, otherwise it is train. Okay, so once you have changed the destination directory, now what will happen is you have to see whether the file starts with cat or not. So if you see here, see all these images, if you have the image of a cat, it starts with the name cat. Okay, so it starts with the name cat. That is an important thing here. Okay, so you can see all these images are of cats and they all start with the cat. Now if you go for dog, here you will see these are images, they start with the name dog. Okay, so what we will be doing is we will be actually using that for our benefit. For our benefit we will be using that. So we will be checking if our file name starts with cat. If it starts with cat, our destination will change to dataset home, that is dataset dogs versus cat. Here dataset dogs versus cat. Let me change the color, let us understand. So let's suppose our image is a cat image and your destination directory is train. Okay, so you haven't changed that. So you have dataset home dogs versus cat, that is followed by a destination directory. Destination directory is train and that is followed by cats. Okay, so now you have the other folder here, cats, and in that you will be saving your file. So this will be cat.0.jpg. Okay, so that is what this means. Let's go one more time. Okay, so now once you have the destination, you are just copying the file from the source to destination. So what is your source? Your source is basically your directory, your actual source directory, that was the train directory, and the file name in it. So that is your source. You will be copying the source from source to the destination. That is what this means. Okay, so let us go one more time and let's understand. So let's say you have an image of a dog this time. So first of all, what will be your source directory? So your source directory is train plus file name. So let's say my dog photo is dog.3.jpg. So now what I will do is, here I will be first identifying my src. So src is basically train slash dog.3.jpg. So this is my original source part, from where I will be moving. Now the second part is your destination. So how will you get the destination? Let's suppose this time your random value is less than the validation ratio. Okay, so your destination directory is test. So in that case, your actual destination will be dataset home, that is datasets dogs versus cat. Here that is dataset dogs versus cats, here that you have. Nice. Then you have destination directory. Your destination directory is this time test. So you go here, and finally the file starts with dog because it is dog.3.jpg. So it starts with dog, so you have plus dogs here, so it will go here, and in here will be your file name. File is basically dog.3.jpg. So the whole thing will be dataset dogs versus cat. Here you will have the test folder. In the test you will have dogs, and in dogs you will have dog.3.jpg. So what that basically means is, now using this code we will actually differentiate the original data, the format that we had, into this data format, this directory format, and all the images will be saved in this format. Okay, so this is what I mean. So if you look here, let's say you will see all those are just cat images. We'll see about that. Okay, so it takes some time to load, but yeah, so that is what we will be doing first. See, all these are cats. Choose any random image. See, this is an image of a cat. So now that we have finally made this whole thing, okay, so we have finally made our data set and we have finally distributed our data in the data set format that we wanted. By the way, copy file is used to copy a file from one position to the other. Okay, so that is what we are using here. And shuttle is basically to perform all in OS operations, so copy file or checking what the file is, changing the file, moving directory and everything, you do that from copy file. So now our data has been formatted, so data is ready for training. Now this is the important part. See, how you are feeding the data in which format is also very important. Hence you should know how to actually use the data and in which format to use it. So now that we have it ready, the next thing that we will be doing is we will be preparing our model. Now the data is there, so the next thing will obviously be the model. I mean, there is no doubt about it. So what we will be doing is we will be using VGG16 for transfer learning. So VGG16, so you have here, wait. So in models also you can get in Keras applications VGG16. Okay, so in Keras applications, so these models, you have the model structure, you have trained these models, you have the model weights, everything is there. You can just call it in Keras using applications.vgg16. Now you have the model, you can create it in this format. Include top equal to false. What this means, this is an interesting thing. Okay, so when we were talking about VGG16, right, or say any architecture, so any CNN architecture when we were talking about, right, so the one thing that we had always was, see, you have the architecture one after the other, you have CNN, this is followed by, let's say, max pooling, and so on until unless you get to the flattened part, right? So you have the flattened part and then this is followed by dense layers, dense and another dense layer, maybe a third dense layer, whatever, right? So this was how your basic CNN architecture was. Whichever architecture you take for now, VGG16, AlexNet, ResNet or anything, you can understand that is the whole structure, right? So what this whole thing about here, include top equal to false, this, what this means is basically that you are making your model ready for transfer learning. So everything after this CNN, so before flatten, all these things will be there. Everything after flatten is known as top or bottleneck features. So these layers that you have from flatten, so flatten, which is followed by dense, which is again followed by dense, these are known as bottleneck features. Okay, so whenever you see this include top equal to false, what this means is I am taking all the feature maps that I am getting from the architecture. So you have the architecture here, this is followed by another thing, this is followed by something else, and then finally you have this flatten here, and once you have flattened, you have fully connected and fully connected layers. Okay, this is how your whole structure is. So everything before the flatten, this is known as the main structure or the stem structure. Okay, and here everything after that or from there is known as bottleneck features. So we all know when we are doing CNN gives out feature maps. So what I was saying is, if you remember that when during transfer learning, what we do is we actually understand these feature maps, right? We understand what is happening in these feature maps, how these feature maps are created, and we get these feature maps. Once we get these feature maps, we can actually train the model for our benefit in the way we want it. Okay, so that is what feature map basically means. So what include top does is it includes these layers. Okay, so if I am training this for ImageNet dataset and I already have the weights, in that case I have to do include top equal to true. But there is no model that has been trained for dogs versus cat. So I am doing everything from scratch. So in that case, what I'll do is I'll keep include top equal to false. So I will not include these layers. These layers I will add on my own. I will write the whole I will write the whole structure about these layers, and these are the layers that I will use for training. So everything before that, these I will not use for training, these I will include as is with the weights. Everything after this here will be used for training. Okay, so these are the ones that I will use for my particular task. This is the whole thing about transfer learning. This is important. So include top equal to false, and you define the input shape. Obviously, if you remember, VGG 16 has an input shape of 224. So 224, 224, 3, because we have RGB images here, right? The dog and cat images are RGB. So now here I will be defining, okay, now I have not included the top part. Okay, this I have removed, but now I have removed this, but at the same time I have to keep here these layers. I have to say, okay, these layers are non-trainable layers. So these layers here that we have, these are non-trainable layers. So these layers, since they are non-trainable, I have to mention that they are non-trainable. So I'll be using whatever weights were there for the earlier model training, for the ImageNet model. I will be using those weights. Only these part will I be using for training. So include top is false. So now my model just looks in this manner. So this is my whole model. In this model, what I will do is I will keep all the layers for training equal to false. So here you can see, for layers in model.layers, layer.trainable equal to false. So all my training layers I have kept to false. So now what my model looks like is basically CNN followed by CNN followed by CNN architectures, and here I am getting all the feature maps. Okay, so this is basically my whole structure about different about the models. And in this model, what I am doing is I am keeping all these layers as trainable equal to false. So these layers are non-trainable. So that is what I am keeping. Once that is done, the next thing that I'll be doing is, now these parts, since this part of the model has been defined and it has been defined that the training paths will be set to false, now my time has come to actually write this part of the model on my own. So this part is there. Here you have to first flatten out all the feature maps, and you have to follow it by fully connected layers. So now what I am doing is I am flattening out the layers, the final layer, and I am adding one dense layer which is of 128. Activation is relu, and kernel initialization is he uniform. So you might remember all of this hey uniform and everything. We talked about this. We even talked about it in the last time when we were talking about MNIST dataset. So I am not going to go over that. So you have kernel initialization as hey uniform, and you have an activation of relu, and then you have 128 neurons or 128 units that you will be using, and you have this is flat one. So that means after flattening out, you will be passing this into the dense layer, and once it has been passed, we will be using dense layer. And this time here, if you see, you have 1 unit, since you have just one prediction here. See, so my final thing is just one prediction here. Okay, so this is a softmax, and it will predict either 0 or 1. Okay, so that means whether this is sorry, not softmax, my bad. Since you have just one prediction here, you will be predicting about sigmoid. So softmax is basically used when you have multi-class labels and everything. When you are using binary, you have to stick with sigmoid, and the sigmoid will be telling you whether this is 0 or 1, the label. So whether it is a class cat or a class dog, that is what it means. So you will be using sigmoid, and hence you have 1 unit here. So now the final thing is you have to make the whole model out of it. So your final model is basically model, input is model.inputs obviously, and output is the final model. So here you are defining your model all over again one more time. So now this can be used, everything as one together, right? Now once that has been defined, now you can define your optimizer. So I am using SGD here. Learning rate is 0.01, momentum is 0.9. So momentum, if you remember, basically we have talked about it also, but momentum basically helps in better convergence of your gradient descent or optimizer. So you have finally you will compile the model. Obviously now that you have whole defined your model architecture, the next thing that comes is to compiling the model. So you will compile the model, you will define your optimizer, you will define your loss and metrics. If you remember last time we did MNIST using categorical cross entropy. Since this is a binary class classification, so we will be using binary cross entropy, and the metric is accuracy as we had in the last time. Here also if you see we used Adam there for optimization, we will be using SGD here, stochastic gradient descent. So we have done the whole thing, we have defined the model, we have made the data as it was. Now the next part comes is the training part. But it is not that easy to just put the data of the whole thing. See, you have to remember a few things here. If you see the data set, it has what? Many data points, if 60,000 or something data points, right? So if you think about this data points, if you totally put this into training, right? So you cannot do that. The reason why is if you put the whole thing into training at once, what will happen is basically your RAM will not be able to handle this much data. So for training what happens is you load the whole bunch into the RAM and then it goes for training into the model. But if your RAM is like, I don't know, 8 GB maybe or 16 GB, it gets kind of difficult, it might lag, it might cause problems. So what we do is we do not load the whole thing into the RAM. So now you might be thinking, well, MNIST also had 60,000 data sets. Well, yes, MNIST also had 60,000 images. But if you remember, MNIST has 28 cross 28 as the size. Here, your images will be 224 cross 224 cross 3. So loading 60,000 images all at once into the RAM so that you can go for training is not the most viable option. So you have to think of something else. And obviously you might be thinking, what about batch size? So batch size is good. Batch size, what it does is basically, see, you have your images here, you have to load the whole thing into the RAM, and batch sizes here, what RAM will do is it will load everything into your model in batches. So this is where, this is where batch size comes in, but we are having problem here, we cannot load the whole image into the RAM. Okay, that is a lot for our RAM to handle. So what we will be doing is we will be using a generator. So let us talk about the generator. So what generator basically does is, generator helps loading images into the RAM in batches. So this is where generator comes into help. So when you have images of some format and you cannot load the whole thing into the RAM because you know your RAM will not be able to handle it, and even if you load your whole thing into your Google Drive, even then you have limited RAM. So it is not possible. What will happen is if you load more than the RAM can actually take, what will happen is here you will get a RAM crash error, and this happens a lot, believe me, this happens a lot. And it is just 12 GB RAM, so you won't be able to handle it. So what here is where image data generator comes into rescue. What it does is basically it loads the images into the RAM in batches. Okay, so we can define how much of the image gets loaded into the RAM at once. So here you have image data generator. So this data generator, it also has some other features. Okay, so image data generator has, so your data generator, it has some features of augmentation as well. So in image data generator you can define what augmentations you want and you do not want. So let's say you want a shift, you want a change of color, or let's say you want a change of shape, you want some crops, you want some clippings and everything. So that part also comes with the data generator, which is a good thing, because if you were in TensorFlow you had to create this whole thing on your own, but in Keras you have data generators to do that. So now what augmentation will basically do is it will increase your images. So you will have so same image will be, let's say, mirrored, at the same time it will be flipped or anything. So a lot of things can happen, crop, or let's say it is rotated. So your same image will look in many different formats, and hence your data set will increase. So let's say I have an image here. Okay, so this is an image of a cat, and here you have the cat's tail. So if you mirrored this image out, it will look something of this format. Now the tail is here. So although this cat is the same, but your data has increased, right? So this is the whole thing about augmentation, and you can do augmentation with image data generator. That is the best part about it. Okay. And here you just define the mean. This is nothing basically. This helps to make sure your data remains centralized, okay, normalized. Now once you have defined your data generator, the next thing that you will do is, now see, you have your data generator. The next thing you want to do is, you have the images also in particular folders. Now the thing that happens is, you have to extract these images and do it, and load it in the RAM so that it can fit into the model. So that is now your whole task, right? So to do that, so that it takes images from your directory, you have this flow from directory, and this is a part of your data generator. Okay, so your image data generator you can define. In that data generator you have a part flow from directory. So what flow from directory basically does is, it takes all the images from your directory in batches, and then it creates a generator, okay, or iterator, whatever you might call it. So this iterator, what will happen is, let's say you have 1 2 3 4 5, okay, you have 5 6 7, okay, you have 7 images suppose, and you have an iterator, and let's say I have defined the iterator size to be 3. So you will have the first 3 images go in, you will train that image. In the next time your iterator will start from the 4th image. Now 4th 5th 6th will go in, right? So that is what this does, is your flow from directory actually creates a training iterator. And in the same way, I'll be creating a testing iterator also, but this time the testing iterator will be from the directory test. So that is why you had the training and testing folder. Now do you understand? We are using training only, and in training we have the training and testing. The testing will be used for validation here. So flow from directory basically is used so that your images can flow from the directory into your training iterator. Now you can define other things, that is your class mode. So what kind of classes mode that will be using, since you have a binary class classification, so you will be using binary. Then you have batch size, and you have the final target size. Okay, so target size is basically what size the images will go in. So it is 224 cross 224. So that is what we are defining, and you have the batch size. So I am not going to run this because it takes some time. So what you can do is, basically you can try and run the whole thing, and you can get these values. Then you have, after you have created the whole thing, now see, this is not like normal data fitting that we were doing model.fit. Now we have created iterators, generators, and you have to fit these generators. So Keras has this option of fit generator. In there you can fit your training data set. Once you fit that, you can define your steps per epoch. If you remember, I have talked about steps per epoch also. Steps per epoch is, as the name suggests, the number of steps you have to take to complete an epoch. So let's say I have a batch size of 64 and I have 640 images. So my steps per epoch is obviously 10 in that case. So I'll be using 64 images first time. The next time I will be using again 64. Then third time again 64. So I am taking 10 steps to complete the whole 640 images, and hence after completing this 640 images I'll be completing one epoch. So that is basically what steps per epoch is. And now that you have that also defined, you have your validation data, you can give that also. Then validation number of steps, again that is steps per epoch but for validation data. And you can define your number of epochs, and verbose equal to 1. I like to keep verbose equal to 1 because it gives you all these values. Now you can see here the loss keeps on decreasing, and you have the validation loss here. You have 97%, 97%. So it keeps you close to 97%. It does not go more than that. Okay. So that is your validation accuracy. You have your validation loss here, and then you have your train loss and train accuracy. Now I am plotting the whole thing. So like you can see here, I ran this whole thing for 10 epochs, right? I would suggest you to run it for 5 epochs. The reason why I am saying this is, you can see here what is happening. So here what is there is, see, you have your loss, this is the training loss which is in blue, and then you have your testing loss here, which is in orange. Testing, no, validation. So you can see here, see, your training loss has decreased by a lot, but your validation loss has not decreased by a lot. In the same way here, your training accuracy has increased by a lot, validation accuracy has not. So you would have ideally stopped it somewhere here in the middle, like in 5 epochs or something, when you have achieved whatever results you wanted. Okay, so since I let it run for a longer time, what has happened is it has kind of overfitted the whole model. So that is why I would suggest to run only for the time that is being used. Next, I have done this. Okay, now if you can see, every epoch takes me 170 seconds. I do not want 1700 seconds to be used to run the whole model again. So I'll be saving the model. So I save it as final model.h5. Now what I'll be doing is, let's say I am loading an image. So this is one particular image that I am loading. So this is dog 6691. Okay, so that means our label is a dog. So let us find out whether it predicts the right answer or not. Okay, so model is not defined. Let us load the model. So like you can see, it takes some time to load the model. So once it has been loaded, we will be able to work this. The reason why it is taking this much time is, see, we are using VGG. VGG itself has 16 layers. So on top of those 16 layers, we have added another 3 layers. So it takes some time because the weights are a lot. Now that we have loaded it, let's check out. So when you are predicting for the first time, right, it takes some time to actually load the whole thing and understand the whole thing. But yeah, from the second time on, the prediction becomes super fast. By the way, let us look here. So you have loaded the model. Now you are loading the image. So you have loading image using load image. Load image is in keras.preprocessing. So keras also has another thing of pre-processing. In pre-processing, what happens is you can load images. So this helps in pre-processing of images. So once you have the image, you can load the image using keras.preprocessing.image. Okay, and now you have to understand that we are feeding into the model arrays. Okay, so you have to load the image and you have to convert the image to array. Once that has been converted, obviously you have to reshape it. So the first number here, it denotes the batch size, if you remember, and this is the actual image size that we are feeding into the VGG. If you remember, we kept the target size as 224, 224, converting it into float 32, and then subtracting out the mean from it. If you remember, we kept the mean here when we were doing, yeah, so in data generator we kept a mean, so we are subtracting out that mean here. So that is what we have done. Once that we have done is, we will now put the whole thing into predict. So it is important that whatever changes you have done to images before you were feeding it into the model, you need to make sure you do the same changes when you are predicting it, because the model is only accustomed to those changes, right? So something new, it will give some wrong results. So here 1 means dog and 0 means cat. So it has predicted 1. So you can say, okay, so your model actually is working. This is the whole thing about it. So see, the second time when I ran it, it was way quicker. So the first time it takes some time. From the second run, it becomes fast. So this was our very first project on cats versus dogs. But yeah, that's it. I hope you enjoyed the project and keep learning.